Start. Okay. Welcome to IITK Temple of Learning. Good evening to all of you. I take this get through questions on the structural analysis. Let us see the we discuss some important topics which are likely to come in the exam. Let us see first one, analysis of statically determinate trusses. There we have learnt how many ways are there to detect whether member force is 0 or not. There are 4 ways. One is to if 2 non-collinear members are there with no external loads at the joint, forces in both members are 0. If 3 members are meeting, 2 members are collinear, force in the third member is 0. Then if panel shear force is 0, force in the inclined member in that panel is 0. Fourth one is if the deformation in any member is 0, then force in that member has to be 0. That is what we have learnt. In addition to that, and in method of sections also we have seen how to cut the members. We should not cut more than 3 members as far as possible. Under special cases where it is not possible to cut only 3 members, we cut more than 3 members also to find force in any particular member. One such way of cutting the members we want to see here. So this is the introduction to that determinate trusses forces. Now we have a truss like this. We want to find force in the member CD, force in this member CD. So the first task is to find the support reactions. W here you will get VA, WB by L, 100 into 4 by 6, and here VF, 100 into 2 by 6. But our task is force in the member CD. We are not interested in any other member. So what we do for that is, we will cut the member CD such that by inspection we will be able to find what is the force in the member CD. For that, if you decide to cut say like this, say this way, like this we are cutting, let us say. Now we have ADE. This is the free body diagram of ADE, we want to take it. See, in the process how many members are cut? 1, 2, 3, 4, 5, 6, 7 members are cut. I mean 7 places. Out of that 2 members are cut at 2 places. So they get cancelled. Supposing that if I am taking free body diagram of this truss within the dotted line. So on that within the truss what others are doing you have to show. If you show that this force, let us say compression, this is compression, same member, this is also compression, they get cancelled. Let us also assume that this is also compression, this is also compression. So these 2 members are cut at 2 places. So they get cancelled, the nature forces get cancelled. Now if I take this free body diagram, this is VA upward, some force was there. This is, I will say, downward force in the member AB. Then this is also, I am taking this free body diagram, this, let us say force in the member EF. Now you see, 7 places are cut, these 2 are getting balanced, these 2 arrows, this is some arrow mark I have shown downward, upward, don't like it, upward, downward issue, doesn't matter. Only one horizontal member now is cut, this one. So now if I take this member, let us say force in the member CD. See, these 2 vertical members have no X component. Then FCD, who will balance? Nobody is there. So FCD has no choice, it has to be 0, because I am writing sigma x is equal to 0. Cut the truss as shown in figure. From free body diagram of ADE, if you take it, if I take sigma x is equal to 0, right side positive, left side negative. Only one force is there, FCD has to be 0. So can be a 2 marks question, likelihood. In addition to the things that you have studied, this way of cutting is an extra concept that we must have an idea. So this is about the trusses, method of sections, method of joints, how we should cut the members. Now let us see the second question. Deflections in statically determinate trusses, frames, beams, this is what we have studied. Now one question is, for the truss shown in figure, if member AB is short by 10 mm, rotation of the member BC is, why it is short? Maybe fabrication error, the welders that you asked them to cut it, instead of 2000 mm he cut it by 1990 mm, 10 mm short he cuts it. Now in the process all other members are cut properly, implied meaning is that. Okay, so we have the rotation of the member AB. Theta, we wanted theta BC. This is summation of PKL by AE. If PL by AE values are given, I can take K delta directly. Okay, delta of AB only is given because all other members delta is 0. So KAB into delta AB. This is minus 10 mm. Minus 10 mm. So KAB you have to find by applying the force. See KAB, how much you will get it? You have to apply unit couple. Theta BC means you have to apply unit couple. Here itself we can show, because we don't have to draw a separate diagram. Apply unit couple here. How much you have to apply? This A value is 2000. 1 by A. That means you will get 1 by 2000 mm. Power minus 1. Here also 1 by 2000 mm power minus 1. The table and etc. not required. Whatever in the regular classwork we have written at tables and finding all the things, that is for the beginners. Now directly we are solving the problems. Now you see 1, 2, 3. 2 are in line, third must be 0. Right side, so it should be left side. Away from the joint, 1 by 2000. All other members you don't have to find because you require only KAB. What is KAB? 1 by 2000. So you will get minus 10 by 2000. In other words, 1 by 2 means minus 0.5 into 10 to the power of minus 2 radian. Negative sign indicates what? Anti-clockwise. Indicates that theta BC is opposite to unit couple. That's all. 2 minutes time. This is our task. Supposing that even this much time also you are not getting in the exam, only 10 seconds like that is there, say. That is called graphical method. How will you find it? 10 mm short, that means when you stand at A, look at B, it moves left side. 10 mm short means, so it rotates anti-clockwise. All other members, no displacements. So you can take the second method as the graphical method. 0.5 into 10 to the power of minus 2 radian means opposite to unit couple means what? Anti-clockwise. That is anti-clockwise. So 0.5 into 10 to the power of minus 2 radian anti-clockwise. Like that. Okay? Yes. Now supposing that if this idea you cannot get it in that time, second way also is there to get the solution quickly. Graphical method. See here, this is the member BC. BC. Length is 2000. B moves to so B, see this one, AB short by 10 mm, that means I can say minus 10 mm. He doesn't tell anything about B, DC etc. That means it's not moving in any direction, it's as it is. So when you stand at here, look at B, 10 mm short means B moves leftwards, C will remain there only. So if you show that it's moving leftward by 10 mm, then its new position is like this, deflected position. B has moved to B dash, this is 10 mm. This is already given. Now this is the rotation anti-clockwise, theta BC. Tan theta BC is approximately equal to BC by 10 by 2000. Directly you can get it 0.5 into 10 to the power of minus 2 radian anti-clockwise. So this is how we will find the rotations of the truss members. You can also find displacement, you can also find relative displacement, you can also find rotations for the trusses, determinate trusses. You can also find deflections in the determinate frames. Let us see the next question. What is the horizontal displacement of joint D? You are applying 10 kilonewton here. For the trusses, that is the process. Okay? AB length 4 meters, BC also 4 meters, CD also 4 meters. Flexural rigidity EI 1600 kilonewton meter square. For all members, assume that it is constant. So when you are using this Castigliono's theorem 2 to find the displacements in the determinate trusses, frames, beams, we have to know that not more than 2 segments they will give you in the exam. 1 segment it will become 0. Now if I take this truss, this frame, what is the process? Delta HD if you want to find. For frames, this is the formula, mx into m into dx by ei. So, we will take those values, mx values, m values. In the first step, you will find mx and m values. Second step, multiply them. We have 2 minutes time. See here, we will write that first step. Mx and m values. Hinge roller, that means it is a determinate frame. Applied load is 10 kilonewton, A, B, C, D. If you apply 10, reaction HA is also 10. This length is 4 meters. Now you see this 10 together forms a clockwise couple. To balance a clockwise couple, anti-clockwise couple should develop like this. VA is 10 down, VD is 10 up. Then this is MX diagram, we can say. Means from this you will get MX calculations. Then small m. This point let us say A, B, C, D. You are applying 1 here and this one has no units because A here at same level. This also must be 1. Since they don't form any couple, VA has to be 0, VD has to be 0. Now, when you want to find the Benjamin diagram values, you will stand here. Go inside the frame, stand here, take a section XX at a distance of x. To decide whether a sagging bend moment, hogging bend moment is there, this section XX. Now when you want to find here, say, you take a section XX, take x from here. Time will be saved for us. Same thing here. Take a section XX. Wherever you are taking a section in the MX diagram, here also same place you have to take it. This also section XX, let us say at a distance of x. Here also you stand here at a distance of x. So this is small m diagram. Right? So now in the next step you have to multiply them. Second one. So delta HD mx m dx by ei. You will take member mx m multiplication. Member mx m integral of mx m into dx by ei. See here, for the first member dc, mx is 0, dc mx is 0, you don't have to worry about this one because product will have to be 0. Next, second member cb, stand here, look right side. This is upward force, so plus 10 into x. Here 1 into 4 plus 1 into 4. This total length is 4 meters. So plus 10 into x, this is CB member. Mx is plus 10 into x, m is plus 1 into 4. Limits of integration are 0 to 4. 4 meters, full length is valid. So mx, 10x, m 4 into dx by ei. 40 into x square by 2, that means 4 square by 2. (16) into 2, 320 by ei, right? Similarly, AB member. Now AB member you will take our starting point here, A to B. So plus 10 into x plus this VA0 plus 1 into x. It is not same because both members structure is not symmetrical. So plus 10 into x plus 1 into x. AB. So plus 10 into x, this is plus 1 into x. Limits of integration again. So 0 to 4, 10x into x into dx by ei. 10 into x square means x cube by 3. So 4 cube by 3 ei. 640 by 3 ei. These are the individual contributions. First member is 0, delta HD. If you add them, 320 by ei plus 640 by 3 ei. 3i common factor, 3 into 3. 960 plus 640 by 3 ei. So delta HD you will get 1600 by 3 ei, right? So ei has given 1600 kilonewton meter square, right? So this is the usual process, mx and m values multiplication, right? This is the thing. So 1600 into 3 into ei, 1600 kilonewton meter square. 1 by 3 means 0.33 meters. That means into 100. So delta HD is 33 centimeters. (33.33 centimeters). Like this. Just observe the process. Allotted time 2 minutes in the exam. Horizontal displacement, they will give you ei values. Okay. So delta HD. First you will find mx and m values. You are standing here, here also you must stand here. Means symbolically you will stand here. To decide whether it is producing sagging bending moment or hogging moment, go inside the frame, stand here, look right side. Here also go inside the frame, stand here, look right side. Here go inside, stand here, look right side. Here go inside the frame, stand here, look left side. But you must go inside, stand here, left side. That way if you follow, your strength of materials sign conventions will match. Sagging positive, hogging negative. Okay. So this is about the frame. Remember that only 2 segments will be there in the exam. More than 2 segments means we cannot complete in our stipulated 1.5 minute time. Right? This is about the truss is over, frame is over. Let us see a beam. a simply supported beam. Find vertical displacement of C. Again, two segments only must be there. Then only we can complete in time. This is a beam. Assume that you have applied a load W. This point, let us say A, B, C. This length is L, L. This is 2I, I. Right? Allotted time, 1 minute time, let us say 2 minutes time. Vertical displacement of C. So we have the reactions are what? VA is W by 2. VB is also W by 2. See, two segments are there, AC, CB. Now if you want to find vertical displacement of C, we will use the unit load method or Castigliano's theorem too. Both mean the same. This is the formula, mx m dx by EI. Okay, now mx if you want to find, you can take a section xx here at a distance of x, and also here at a section xx at a distance of x. See, only two segments. Strain energy in two segments only we are finding. Here strain energy stored due to bending moment. Frames also strain energy due to bending moment. But in the truss first problem, strain energy due to axial loading. There is only difference. Okay. Now if you apply W, W by 2. If you apply unit load, 1 by 2. So quickly you can get it. So you don't have to draw a separate diagram also. Directly we can take it. Member this will, you in the exam you have to use the strain energy method or unit load method if you have only two segments like this. Then only your stipulated time you can complete. Member mx m see member mx, now small m, vertical displacement of C. This you can use it for beams, trusses, frames. mx m dx by EI. So member, first member is AC member you can take. AC member, bend moment is W by 2 into x. Now m due to unit load, if W becomes 1, here it becomes 1 by 2. So this becomes x by 2. Now limits of integration are 0 to L. Wx by 2 into x by 2, mx into m into dx by EI. So W by 4EI, x square means x cube by 3, L cube by 3. So you will get WL cube by 12 EI. This is the contribution of the segment AC to the vertical displacement of C. Similarly CB, BC. This I value how much? AC member I value is 2I, 2EI. This you have to be careful. 2EI, that means here you will get 8. Eight into 3, 24. 24 EI. Next here, BC segment. Bending moment is Wx by 2. due to unit load x by 2. Limits of integration again 0 to L, Wx by 2 into x by 2 into dx by, in this segment EI value same, means half of that. So you can take simply EI. So this you will get W by 4 EI, or otherwise directly we can write it half of that. See, here 24 EI got it, here that 2 is not there. So you will get, if you multiply this by 2, WL cube by 12 EI. These are individual contributions of the segments to the vertical displacement at C. So add them. Common factor 1, 2, 2 plus 1, 3, 3 WL cube by 24 EI. In other words, it becomes WL cube by 8 EI. See, only this much. This is the beam, 2 marks, this is the solution. So in the exam you must try, if 2 segments are there, check if you can manage it by strain energy method when you are to find the displacements. Next. I think this is done with. So 3 examples. Now let us see influence line diagrams. A 10 kilonewton load is moving from left to right on the beam shown in figure. During the passage of load, only one load, because you have to find sagging bending moment, maximum hogging bending moment also. So can be given for a 1 mark question, maybe a 2 marks question, allotted time 30 seconds. Right? A 10 kilonewton load is moving from left to right on the beam shown in figure. During the passage of load, maximum hogging, maximum sagging, bending moment at D, or sagging and hogging bending moment we want to find. Influence line diagrams, to draw ILD for reaction, shear force, bending moment we have known. To draw ILD for reaction, remove the support, hold it, lift it by 1. Then the virtual deflected shape of the beam itself is the ILD for reaction at that support. ILD for shear force means wherever you want to draw ILD for shear force, cut the beam at that point, means release the shear force at that point and apply unit virtual displacement. Then the deflected shape of the beam is the ILD for shear force at that section. If you want to draw ILD for bending moment at any section, whether it is a determinate or indeterminate structure, but it must be linearly elastic structure, then what you have to do, release the moment at that section. Releasing the moment at that section means assuming an imaginary hinge at that section. So, and apply unit virtual rotation. So when assume an imaginary hinge here, apply unit virtual rotation. You cannot rotate it here anti-clockwise because it cannot come down, because A and B are fixing it. So it cannot rotate. It must, in a statically determinate structure, assuming an imaginary additional hinge means it becomes unstable structure. So it will only undergo rigid body rotation and translation. So if you apply unit rotation, it will go something like this. Like this is a unit rotation, it can go down, then this will go up like this. This is the ILD for bending moment at C. ILD for bending moment at D. Okay. Now this is theta. Then the deflected shape of the beam itself is the ILD for bending moment at D. What this ILD tells you is whenever you are moving from A to B to C to D, bending moment at D is 0. Only when the load crosses D, then there will exist bending moment at D. This is minus because going below reference line. This is going up. this is positive. Okay. Now see, what is the displacement? 3 into 1, 3 meters. Now similar triangles you have to take. For a distance of 2 meters, this is 3 meters. Here also 2 meters is there, then it has to be 3 meters. So to get maximum hogging bending moment at D, load must be kept at E. To get maximum hogging bending moment at D, load should be kept at E. So maximum hogging bending moment at D. Keep the load here. Load is 10 kilonewton, 10 into minus 3. Or in other words, 30 kilonewton meter hogging bending moment. Now if you want to get maximum sagging bending moment, load should be kept here. This is 10 kilonewton, 10 into plus 3. This point, let us say G we have written. So to get maximum sagging bending moment at D, 10 kilonewton load should be kept at G. So you will get maximum sagging bending moment 10 into plus 3. So 30 and 30. See here, 30 and 30. 30, 20, 20, 30 like that. Why like that? There is a likelihood mistake is this one. 3 meters, so 3, it is only 2 meters. If you write say 2, then 20 kilonewton meter also option will be there. So that's where you have to be careful. So on the influence line diagram, this is the case. Why rotation anti-clockwise? Why not clockwise? This is clockwise only we rotated. This one, when load is here, then at D you should get hogging bending moment only from strength of materials. So here it must be negative ILD. So that's why we have done below reference line. For it to be below reference line, it should be clockwise. That's all. No great reason. Okay? Next. See, for the continuous beam shown in figure, to get maximum sagging bending moment at D, the spans to be loaded are. So first we have to draw the influence line diagram for bending moment at D. That ILD will tell us where we have to keep the loads. Now see, to draw ILD for bending moment at any section in the indeterminate structures, at that point we have to assume an imaginary hinge. Assume an imaginary hinge. Now you have learnt in SM that if we have a beam like this, say, how to build the ILD I am showing, this is the D or any other point. If load is, this is the intermediate support, next to that support if load is downward, say, then it will hog, or here it is there. On the adjacent span of the intermediate support, if loads are there, it will only hog. That means adjacent spans, you must draw negative ILD like this, it should go downwards like this. First you fix this part like this, negative portion. Now you draw that as a continuous member. That means this is a continuous member, so it will go up, down, up. Here also up, down. Now you see, below reference line if it goes minus, above reference line plus, minus, minus, plus, minus, plus. So like this, such that the rotations here, here, if you drop the tangents, this theta will be 1. This is your ILD for bending moment at D. If you want to get maximum hogging bending moment at D, you must load adjacent spans and alternate spans. How do we know? ILD is telling like that. If you want to get maximum sagging bending moment, question is sagging bending moment, then you must leave the spans adjacent to the support and load alternate spans. That means you must load maximum sagging bending moment if you want, positive bending moment. This is positive ILD, this is negative ILD, this is also positive ILD, positive ILD. So to get maximum sagging bending moment, BC, EF, GH you have to load it. BC, EF and GH. If at all they ask you to get maximum hogging bending moment at D, you must span AB, CD, DE, FG. Where negative zone is there, if you get it, maximum hogging bending moment. So this one, to get maximum hogging bending moment at D, because in the exam we don't know whether they will ask you to get maximum sagging or hogging. This is to get maximum sagging bending moment at D. This is similar to what you have studied in RCC. In RCC you have learned that at any intermediate support of a continuous beam, if you want to get maximum hogging bending moment, you must load adjacent spans and also alternate spans. If you want to get maximum sagging bending moment at any intermediate support of a continuous beam, what you have to do? Load next to the adjacent spans. Next to the adjacent span means for the support D, adjacent spans are this one. Next to adjacent spans means BC, CD. So load next to adjacent spans and alternate spans. Meaning is this one, BC, EF, GH. Okay. So this is the influence line diagrams for the indeterminate structures. Yes, answer is A. Now let us see why rotation. Okay, that I think oh, so many people are answering A. Good, my dearest. I think you are understanding completely, thoroughly. I think you are revising very well. So happy, my dearest. I think you have revised completely. Very good. Now let us see the moment distribution method. How the questions likely to come. We have a frame shown in figure. Moment developed at A. This is a guided roller support. This is simple support, that means roller support, that's all. Pin also is there, no pin here. This is free end. I am applying a moment of 50 kilonewton meter. Then what is the moment developed at A? Time, say 30 seconds time. In the gate or prelims, scope is only this much. We should not work too much for the structures part in the exam. So questions are very simple. Only fundamentals you must be thorough. Okay? Coming to this one. So whenever you have the far end hinge, far end roller, that's what you have studied. If it is far end hinge, relative stiffness is 3 by 4 I by L, roller support also 3 by 4 I by L, free end 0. That's what we have studied. But after studying that also, you must apply first the rotation, see the deflection profile of the individual members. Those deflection profiles will tell us what is the relative stiffness. Okay? So when I hold this and try to rotate, the deflection profile of the members will be something like this. I am showing them here. Okay, there is a guided roller support here. This is hinge, roller support simply, fixed, free. I am applying a moment of 50 kilonewton meter. This point say A, B, C, D, E. This is a B, C, D, E. Now when I rotate it, how the deflection profile will go is like this. Here, for it to remain like this, here there is no reaction developed horizontally. So it will bend like a straight line. This way it will bend, because there is no reaction in this side. It will simply slide this way, and this will go like this, and this. Straight line it will go. So for this profile, this is for this profile, deflection profile. Okay. If you take this portion alone, when far end is fixed, I by L, so that means this is I by 4. This value is KCA. For this, when far end is free, relative stiffness is 0. Here also far end is, though it is not free support, it is behaving like a free end only, because no reaction developed here, so bend event is 0. Wherever you stand, look right side, bend event is 0, because no reaction. That means here also for the E will go to E dash, KCE is also relative stiffness 0. This is now like a cantilever beam, KCB, 1 by 4 I by L. If this is I by L, this is 1 by 4 I by L. Now you see, with this distribution factors you can find. Distribution factor is, we wanted moment at A, KCA by sigma K. KCA is I by 4. Sigma K, I by 4 plus 1 by 4 I by 4. So you can write it all other members, sigma k it is 0, 16. That means 4 plus 1, 5, 5i by 16. Five I by 16. Here I can write it as 4i by 16. Just to divide easily. 4 by 5. 0.8. So, moment at C for the member CA, distribution factor KCA into M, 50 into 0.8. So you will get 40 kilonewton meter. Either you can do like this or draw the table. Our choice. Moment at CA. Then carryover moment, MAC. Here in this case, this fellow has taken out of 50, this is 40. And this is taking 10. 50 into 0.2 is 10. Then see, this is clockwise. Here also clockwise moment will develop. MAC, half of MCA. Carryover moment is half of that. So 20 kilonewton meter. This is the process. You applied 50. This fellow is strong, 4 times stronger than this fellow. So he took 40, he took 10. If this is 10, here also 10. If at all MBC they ask you, 10 only you have to answer. Out of 10, here half we should not, 5 we should not write it. Clockwise means here anti-clockwise, MBC. You will get 10 only. Here clockwise 10, anti-clockwise 10, because carryover factor is -1. But when foreign is fixed like this, carryover factor is half. So plus 40 means plus 20 only will come. That means 20 kilonewton meter clockwise. See the deflection profile, how it is going. This is the process. Okay, now come to this one. 20 clockwise, so 20 clockwise. 20 kilonewton meter clockwise. C is the answer. सर टेबल मेथड बता दीजिए. फार एंड डिफ रोलर then stiffness value. It's like this. Okay, instead of this one, if I take the table here, we have taken the table, we are familiar with that. Distribution factors is like this. Joint, member, K, sigma K, distribution factor. Okay, let us see now, as we are familiar with that table, joint, member, K, sigma K. Distribution factors are K by sigma K. Which joint we are taking? C. CA. Far end is fixed. I by joint is C. Member is CA. I by 4. Because this is the 4 meters length. 2 meters only it is. Okay. This is I by 2 only. I by 2. I have given 2 meters This is 3 meters we have taken, but okay. Thinking that 4 meters I have written it, but as per the question only we will move it. I 2 meters, okay. I by 2, 1/4 of I by 2, this is 0, 0. I by 2, I by 2. This value now, final result will not change, only 2 meters. This value will become 8 common, 5I by 8. This is 4I by 8. Okay. Now let us fill the values correctly. As per the table, if I go C to A, far end is fixed, I by L. So I by 2. Next, CA is over, then CB. When far end is guided roller support, 1 by 4 I by L, 1 by 4 times I by L. So this you will get I by 8. To calculate sigma values easily, this we will write it as multiply by 4 here, 4 here. 4I by 8. I by 2 is nothing but 4I by 8. Next, CD, CE members. CD, CE members. Relative stiffness is 0. Why? It becomes 0 when, see your far end is free, stand here, look right side, bend moment is 0. That means what? Whatever moment you apply here, moment is 0. If moment is 0 means what? It remains as a straight line. So when far end is free, relative stiffness is 0. Now come to this one. When I apply moment, there is no reaction in this side. Then what is the bending moment at any section here? If reaction is 0, who will give bending moment? That means it behaves like a far end free only. Just because you have a roller support, it is not giving any moment. So it remains a straight line. These deflection profiles will decide what is the relative stiffness of that particular member. Okay? So if I draw the table like this is 0, 0, 4 plus 1, 5. You will get 5I by 8. 4 by 5, 0.8. 1 by 5, 0.2. These distribution factors are 0, 0. It's like this. Now CA member distribution factor is 0.8. CA member distribution factor is 0.8 into 50. So you got 40. That means out of 50, this fellow took 40. Then once this is 40, carry over moment is 20 in the same direction. But whereas if they ask you BC, carry over factor for this is minus 1. If you apply plus 10, here you will get minus 10. Right? If you are able to draw the deflection profile after applying the moment, those will decide what should be the relative stiffnesses of each member and accordingly proceed. We have given you the list. This is 3 I by L, this is 1 by 4 I by L. If we have a hinge support here, we will write 3 by 4 I by L, like that. Fine. Now this is our problem. So 20 kilonewton meter clockwise. I think now you have understood it. Guided roller case E by L, correct. E by L is correct. Relative stiffness now becomes 1 by 4 I by L. Length in question, yeah, now I made it. I have changed that. 2 meters, right? That's why I thought it was 4 meters. Because in the regular classwork for all the problems we took 4 and it went into that like that. So no issues. Now I think understood? Fine. Let us see the next one. For the beam loaded as shown in figure, what is the moment to be applied at B so that rotation at B is 0? How much moment M we have to apply, either clockwise or anti-clockwise, whatever is that, so that rotation at B is 0. So and then such questions come. Rotation at B 0 means where will you make the rotation 0? In moment distribution method, symbolically we will lock the joints so that slopes are 0. Then after that you release them. He is not asking don't release, just to lock it how much moment is required. That's all. So for that we will take fixed end moments. These are symbolically we are fixing the joint. Fix it, fix it, fix it. So you will get MFAB minus WL square by 12. So you will get minus 16 kilonewton meter MFAB. MFBA you will get plus 16 kilonewton meter. Similarly MFBC WL by plus minus WL by 8. W into L by 8. So minus 15 kilonewton meter. MFCB plus 15 kilonewton meter. You see in the process whether I is there, 2I is there, it is not reflecting here at all. Okay? Now fixed end moments. Distribution factors. Actually distribution factors are also not necessary to calculate. Let us see why it will not be necessary. Third one is EMD. EMD means end moment distribution. This is the process we have done, but out of that a small part is asked. End moment distribution. Joint, this is A, B and C. Now distribution factors, this what we have listed it out. Here it is 0, fixed support. Some values are there, we are not interested. Here it is 1. Then fixed end moments. Here you got it minus 16 plus 16. This is minus 15 plus 15. These are all the fixed end moments. To symbolically lock all the joints, you have to apply minus 16, plus 16 if you apply it is locked, BC means minus 15, it will be locked. To completely lock the joint B, you require plus 1. To lock joint C, you require plus 15. But we don't want to fix C, because he is telling only how much moment you have to apply so that theta B becomes 0. It is the question. So release C. Unnecessarily locked that. Release C. So minus 15. When you release that, carryover moment will develop. How much carryover moment will come? Minus 7.5. Now you will get net fixed end moments. Net fixed end moments necessary to lock all the joints to make the slopes 0. Here you are getting minus 16 plus 16 minus 22.5, 0. Now you see. Now to lock joint B, how much moment is required? Minus 6.5 kilonewton meter. If you apply, it is locked. Then what you will do in the moment distribution method? You release, then distribute. Release and distribution is called balancing. Don't release, don't distribute. Just find what is the fixed end moment to make the slope 0 means only sum of this one. So, moment M required to make slope at B 0 is plus 16 minus 22.5 minus 6.5. Minus means what? Anti-clockwise. So if you apply 6.5 kilonewton meter anti-clockwise, slope becomes 0. So 6.5 kilonewton meter anti-clockwise. Like this. That means you have to apply anti-clockwise. He has given some direction like that, say. So instead of completely asking you to distribute end moments, final end moments to calculate, part of that problem, what is the moment necessary to lock it? That means what is necessary to make the slope 0? Means just net fixed end moments will give you that value. So first fixed end moments is in the process distribution factors, waste of time, EMD. Just find this, sum of this will become moment at B. Next, for the frame shown in figure, what is the moment developed at A? Now let us see the deflection profile. We can see this one from this. Easiest way to finish off this problem is like this. $40 kilonewton. This is 8 kilonewton per meter. Because of this loading, if you draw the deflection profile, and if that deflection profile is a known deflection profile, you can directly match the whatever strength of materials formulas you have learnt, you can stick it. Now see here. This will deflect like this. This, because of this load, it will deflect like this. Like this. This alone is looking like a propped cantilever beam subjected to UDL. Because of this load, there will be one reaction. But that reaction will not influence the bending moment curve in that member because axial loads are neglected in MDM. For this profile, when it is subjected to UDL, propped cantilever beam, what is the formula? WL square by 8. So directly you can write W into L square by 8. 16 kilonewton meter anti-clockwise. Either they simply ask you 16 or direction also if you want. (16 kilonewton meter anti-clockwise). See here, this profile will not influence this fellow will not influence this fellow. Because axial forces only they will exert one on the each other, so they have no influence. So it behaves like, each one behaves like a propped cantilever beam. Fine. Next, for the box frame shown in figure, moment developed at A. Such boxes are given, say. Then what we have to do is, it is symmetrical about x-axis and y-axis. Cut here. Symmetry is there. Symmetry is there. Then you will take only 1/4 of the frame. Which quarter we have to take depends on which corner he is asking the moment. So only because it is symmetrical, I can cut this out. Because symmetrical, cut it out. Only take this quarter frame. Then it looks something like this. This is your imaginary frame. This point is A, this point is B dash, this point is D dash. So this you will get KAB by 2. This you will get KAD by 2. This is your imaginary frame. On this imaginary frame, distribute the end moments, which you get the fixed end moments, what you get from the actual frame. Take those fixed end moments, distribute here. Whatever moments you get it on 4 corners, you just replace it with opposite sign. Now you see, if I take it, what is the fixed end moment? This is the process. Only MFAB is enough. WL by 8 minus W into L by 8. How much you will get? Minus 10 kilonewton meter. Then second step, distribution factors. This is for whom? Imaginary frame. So joint member K sigma K distribution factors. Now you see, you take joint member K sigma K and distribution factors are K by sigma K. Now see this one. Only one joint you have to consider. Joint A, member AB dash, AD dash. AB dash is half of the original stiffness. So half of KAB. I by 4. That means I by 8. AD. Half of AD means I by 2. Half of that. Half of I by 2. You will get I by 4. To simplify the calculations, you write this as 2I by 8. Now summation will become 3I by 8. This is 1 by 3. This is 2 by 3. These are the distribution factors. Next, EMD means end moment distribution. This you will do it for the imaginary frame. Joint See here, only imaginary frame we have to do this one. Joint. What are the things here are there in the imaginary frame? B dash A D dash. B dash A D dash. Distribution factors. We don't write anything. Here also we don't write anything because they are imaginary fixed supports. AB dash 1 by 3, AD dash 2 by 3. Then fixed end moments. What are the fixed end moments? MF AB only is there minus 10. Here nothing. MF AB minus 10, 0, 0, nothing here. Then balance. So plus 10 into 1 by 3. Plus 10 into 2 by 3 means 6.67. Then you see carryover moments. Because this imaginary fixed support, you don't show anything here. Now you will get final end moments. Add them. Final end moments. Nothing. This is minus 6.67. This is plus 6.67. Nothing. So moment at A. Plus or minus they will not ask you, simply like that. So just observe this one. Imaginary frame. So this is our frame. First you have to find fixed end moments, then distribution factors, then end moment distribution, final end moments. So 6.67 is the answer. Okay. Now let us see the next one. A three-hinged parabolic arch of span 20 meters, central rise 5 meters, is subjected to a point load of 100 kN at crown. Hundred kilonewton at crown. This point let us say A, B, C. 5 meters, span is 20 meters. Now L is 20 meters and central rise 5 meters. Then radial shear force in the arch at a distance of 5 meters. This point let us say D. X is equal to 5 meters. That means X value is L by 4. Now we have studied in the arches that when the load is at crown, absolute maximum negative bending moment will happen at a distance of L by 4, 0.25 L. If you take a section XX at 0.25 L, keep the load at the crown, you will get absolute maximum negative bending moment at D. Then at the location of maximum negative bending moment, what happens to the shear force? It will change its sign. So when the shear force is changing its sign, its magnitude is 0, shear force value is 0. So directly we can put radial shear force is 0. You don't have to calculate normal thrust means VA, HA, XY components. You take it, find the components along the normal direction and also parallel to that. That much time you don't have to waste it, because load at crown, X is 0.25 L, absolute maximum negative bending moment. We know that shear force must change its sign. While changing its sign, the magnitude of shear force is 0. Okay. Now let us see the next question. For the frame shown in figure, axial force in the member AB. Using portal method of analysis. Lengths are not given, suppose all lengths may be same, you can say. Some lengths are given. This distance, let us say 4 meters. We want to find axial force in the member AB. To find that, using portal method of analysis, what are the assumptions? POC is assumed to be located at midpoint of each beam and column, here, here, here. This is your first assumption, right? Now, if I take free body diagram at this level, above A, like this, below A you take another free body diagram. You take this as a 1, 1, you take this as a 2, 2. Okay? Now, another assumption is exterior, if you have interior columns also. Second assumption is the horizontal shear is assumed to be distributed or divided among all columns such that the interior columns will take twice that of exterior columns, but in this case both of them are exterior columns only. If I take free body diagram above 1, 1, when 40 is acting like this free body directly I am showing here, this is H value, here you will get, here also H, 40 will be shared by this one, so 40 is equal to 2H, that means H you will get 20 kilonewton here, this is also 20 kilonewton here on this free body diagram. If I take 2, 2, above 2, 2 if I take say 20 kilonewton left side, here also left side 20 kilonewton. Now if I take AB is over this point, let us say CDE. ACDE free body diagram, if at all I take it out, this point I am showing you there C. This is C, this is A, this is D, this center point is E. This value let us say 2 meters, this is 1 meter, 1 meter. When you take above 1, 1, this member is exerting on this one H value 20 kilonewton. If I take here, this is I am taking below 2, below 1, 1. So your horizontal force here will act 20 kilonewton. There also 20, we are not interested in that. Here above 2 to only we are taking free body diagram, so don't have to change the direction. This is also 20 kilonewton. Since sigma x is already balanced, H is here, H is here. So horizontal reaction at E, now it becomes 0 from sigma x is equal to 0 consideration. So it simply becomes 0. Okay, this is the from free body diagram of ACDE. If I write sigma x is equal to 0, plus 20 acting at C, minus 20 acting at D, minus HE is equal to 0. This type of analysis you have done in the steel structures also, in the design of battens. This is a built up column you have taken, axial force in the batten is 0, shear force is Vc by Ns, bending moment is Vc by 2n. In the derivation of that it has come like this. So directly if at all you see like this, axial forces in the batten members or axial force in the horizontal members, directly you can write it as 0. The portal method of analysis we can apply only when all joints are rigid, subjected to horizontal loads at the joints only. So those assumptions when you take it, cut it 1 1, above 1 1 you take it, cut it at 2 2, above 2 2 you take it, pluck it out, stick it here. This free body diagram tells you that horizontal reaction at E must be 0. Means the axial force in the member AE. If axial force is 0 means force in the member AB is also 0. Right? It's like that. This is from portal method of analysis. So any one member if they ask you, above and below you take it, that free body diagram and you take the assumptions that are there in the portal method, complete that analysis. Now we want to see what is the static indeterminacy for the frame. Now number of supports. Number of supports are 2, so we have to get 2 cantilevers. 2 cantilevers. So to get 2 cantilevers, how many cuts are required? 2 cuts. This point let us say A, B, C. Now if you have a hinge at the joint itself, how many? It is not a stable cantilever, so you have to make it rigid jointed one. So if you add 2 moments, third moment is sum of the above 2 only. So unnecessarily you are adding 2 reactions, so subtract 2. Now after cutting it, it will rotate, so fix it. Unnecessarily you are fixing it, so release it, so minus 1. Here this is hinge next to the rigid joint. To make this member as a rigid jointed one, I have to add 1 moment, so subtract 1. So now your static indeterminacy is ds 3 into number of cuts. Here number of cuts are 2. 3 into 2 minus number of reactions unnecessarily added to make stable cantilevers. Why should we make stable cantilevers then subtract? That is, if you want to use ds is equal to 3 into c number of cuts formula, it is necessary that all joints must be rigid jointed ones. If they are not rigid jointed members, make them rigid. To make them rigid, how many reactions you have to add? So many reactions you subtract. Then you will get for the actual structure what is ds. So minus 2 at A, minus 1 at B, minus 1 at C. So 6 minus 4, 2 degrees. So this is how ds is calculated. Okay. So this process I have told you, out of all the methods, cantilever method is the best way to get out of the problem, to get out of that problems. Now let us see, for the truss shown in figure, horizontal displacement of joint A. It is a statically indeterminate structure, kinematically also indeterminate. For such structures you cannot use, as I have told earlier, pKl by AE. We cannot use it because it is indeterminate. So if the structures are indeterminate structures in the trusses, you must use the stiffness matrix method only to get out quickly. So for that you require, first this dk is only 1. First point is kinematic indeterminacy. See here at this point dk is 0 because it is a truss element, rotations we will not count. dk is equal to 0, here dk is only 1. Displacement of A in x direction. So dk is 1 degree. So size of k 1 by 1. So now if you want to find the stiffness matrix, that stiffness matrix K will have only one element. K is equal to K11. This is the formula AE by L cos square theta. This is for the member AB plus AE by L cos square theta for the member AC. In this case, AE is constant, 10 to the power of 7 Newton for all members, but length is different. So AE by L, first we will write it in terms of that. AE by length is 4 meters, cos square 135 degrees. See here theta you have to measure in the anti-clockwise direction only. This is your coordinate one because delta AX only is possible. This is theta AB, 180 degrees. Theta AC, that means the other one. This is theta AC, 135 degrees. You must measure from the positive x-axis in the anti-clockwise direction only. So AE by L cos square theta. Here also AE by L means 4 root 2. Why length is different? If this is 4 meters 45 degrees, this is 4 root 2 meters. 4 root 2 into cos square 135. Cos square, this is 180 degrees. This is cos square 180 degrees. For this 135 degrees. This is a k value. So you will get its result. 4 and 4 root 2 means AE by L. AE by 4. This is 1 by root 2. AE by 8. This length I have given. So this will become 8 root 2, right? Cos square 135 means 1 by root 2 square root means 8. So let us see, AB is 4 meters, cos square 180, correct, AE by 4, this length is 4 root 2 meters, cos square 135 means 1 by 2. 1 by 2 into 4 means 1 by 8. Okay, this is the value you are getting. So this value when you calculate, how much you will get? So when you calculate this one, point 338. This is K. Point 338 AE. Now, once K value is known to us, it is a force required to produce unit displacement. But for 100 kilonewton, how much? This is the value. Final force is this much. Force required to produce unit displacement is K. Then for delta displacement is delta. How much force is required? P by K. I can write P is 100 kilonewton by K. Direct, because only one element is there, I can write it as so 100 by 0.338. $295.85. If they give you AE value, say, that values will substitute, otherwise we will leave it. In terms of this we calculate. AE value is given 10 to the power of 7. So if you write that kilonewton when you are writing into 10 to the power of 3 Newton, kilonewton you are converting into Newton, AE you are getting per meter. So AE value is given, AE is 10 to the power of 7. This is when you are calculating this, this was in terms of meter. So you convert into mm, 10 to the power of minus 3. So you will get 100 into 10 cube. So this value works out to be 10 to the power of 6 you are getting. So 29.58. So approximately like this you will get 29.58 mm. Okay, if nothing matches, we will put E value. I changed the dimensions, that's why nothing is matching. Here I have taken 4 meters. With 2 meters calculation I have given this one. So, but it is actually I have written 4 meters. I don't want to change this value. So accordingly this was came. If you say only 2 meters if you take, suppose, then you will get 14.77. Okay, now I changed, I doubled the length, so accordingly it became 29.58. But the process is like this. What is the horizontal displacement of joint A? Since I doubled the length, here also I have to double it. Into 2 when I put it, exactly 29.58 you will get. So, E is the answer. Okay. So, first we will find the dk, just to know the idea of how much we have to, what is the work to be involved. So, k value you have to find, only one matrix you will get, one element you will get it. Now your reading should be like this. 0.338 AE is the force required to produce unit displacement, but this much force I am not applying, I am applying 100. Then what is the displacement? 100 by this you get it, the value. Okay, numericals means this is the scope in the exam, right? I wish you all the best, my dearest. This is, I think, I have covered all the maximum number of topics that are likely to come in the exam. All the best. Good day to all of you. Then, thank you all, my dearest, for listening to all this one. I think I have given you, I didn't waste your time sufficiently. I think I have revised all the important questions that are likely to come. This overall bird's eye view I have given. In detail again, half day you revise our class notes. It is sufficient. Good night all of you, my dearest.